show parameterize the validity of the vectors of nominals. And also this, as I will show later, that as I will show in the next slide, that the Rhombus of mass is given by this form. Yeah, this A and this A are same. Sorry, some kind of character is changed because I made up this slide when I use Windows system, but this is Mac, some kind of character is changed. Okay, next, let me show the phenomenology at the tree level of the theorem of symmetry. Okay, this is the hidden the Lagrangian, which I showed before. And you can introduce the photon field by through these external gauge field, mu. In this way, a bit hard to see, but for example, in the three-flavor case, this Q corresponds to the charge matrix. This is the charge flow term of strange code. And this mu is a photon field. Then you can expand this parallel mu and perpendicular mu in terms of the Pi field. And then actually you get we obtain this is these are the expanded form. Then you can substitute this form here, and then you will get this kind of Lagrangian, which is the higher other term. But anyway, this term corresponds to the biogenetic term, and this term corresponds to the mass term, and this term is the low fiber coupling. And this term is a low gamma mixture, which I will show later, what this mixture implies. And also this is a direct gamma fiber coupling. But then these quantities are written in terms of original three parameters. In this way, m rho is given by the product of the AG square pi square. And 0 here is expressed as AG pi square. And the low fiber coupling constant is expressed by this form, 1/2 times LA times G. And the direct gamma fiber coupling is expressed as 1 minus over 2. Then as you can easily see that there are 4 quantities which I showed, but they are written in terms of 3 parameters. And there is one non-trivial relation, which is called the Roy-Rossi theorem of hidden local symmetry. So that you can easily see that this relation form, okay, 0 is given by the 2 times of this.
学务处报告，学务处报告，下星期一4月7日上午10点到下午1点半，于活动中心3楼体育馆举办2014年校园就业博览会，邀请长庚医院、台塑关系企业、广达电脑及1111人力银行等31家企业莅校参展。相关职缺请上学务处就业博览会网页查询，欢迎同学踊跃参加。学务处报告，学务处报告，下星期一4月7日上午10点到下午1点半，于活动中心3楼体育馆举办2014年校园就业博览会，邀请长庚医院、台塑关系企业、广达电脑及1111人力银行等31家企业莅校参展。相关职缺请上学务处就业博览会网页查询，欢迎同学踊跃参加。
Okay. Okay, then this you can easily confirm this relation. Actually, this relation was known from long time ago, more than 50 years, as a so-called KSRF relation version 1. KSRF is the name of the 4P. But anyway, that this relation is known as a kind of a good relation for phenomenological relation. And also, okay, in addition to this parameter independent relation, we have some parameter A as 2. If you take A equal to 2, you can find this relation for. This relation is also known as a KSR relation, part 2, and phenomenologically well satisfied. And also that if you take A equal to 2, this direct gamma pi pi coupling goes, so direct gamma pi pi coupling vanishes. This property is known as a Robinson dominance for the electromagnetic form factor of the pi. Let me explain that first. Explain this pion electromagnetic form factor. And what is the pion Robinson dominance? And then in the space-like region, in pion electromagnetic form factor is expressed by some of these two contributions. One contribution is photon couples, so interact pion directly, or photon interact pion through Rowe method. Okay, here, this Rowe method, then in the hidden local symmetry model, photon couples to or mix with Rowe method. Then once photon comes, it changes to Rowe method, and Rowe method coupled to pi pi. Okay, then this is parameterized in this way. So this contribution is written in this way. Okay, this low gamma mixing strength is given parameterized by 0. The low pi pi coupling appears here, and this is the propagator. Okay, then using this parameter relation obtained in the hidden local symmetry, you can obtain you can derive this form factor in this way. You just substitute this into here, and you keep only m rho square and a parameter a. You obtain this form. Then once you take the parameter choice a equal to, this part goes away. Actually, this part is nothing but coming from this one. Okay? This g gamma pi pi is equal to 1 minus a over 2. Because then this implies that the photon couples to pion only through Rowe method. And a equal 2. Then this is the meaning of vector method dominance. Okay, then this is regarded as good. Okay, from the long time ago. This is phenomenologically. Okay, next, let me check whether this relation is good, phenomenologically acceptable or not. To do so, we use these as input. Okay, the pi and the Robinson mass, and the rho pi pi decay waves, and the rho going to e plus e minus decay waves. Then you can calculate something. Okay, this parameter, with 0 pi pi and 0. Okay, it comes announcement. I hope it's short. But anyway, if you combine these experimental value in this way, you obtain the 1.15. But the prediction of hidden local symmetry gives this is 1, this should be 1. Means that 15% deviation. I don't know whether 15% is good enough or not, but I think that in the Hadron phenomenology, 15% is good enough. Then, okay, then and also that as I will explain later, okay, that we have higher order terms in the hidden local symmetry. Then 15% is not bad for if we regard this as higher order effect. But then this implies that that's some hope to make a kind of expansion or kind of perturbation starting from the Lagrangian, which I showed as a leading order Lagrangian. Okay, let me show the determination. Yes, the value of the parameter. Okay, that the phi, I use just the experimental value, and the gauge coupling G and A are determined in this way. Okay, I use the rho pi pi coupling and the pi square and the rho square as experimental value to determine the gauge coupling. This is the value, and then put 15% error. As I said that we can expect the 15% error, then I put 15% error here. Okay, then A, parameter A, I use this formula. Using this value. Then this is the value. Determine 2.07. Again, I put 50% error. Then these are the predictions. Okay, of course, that log mixing using this value, and then you can calculate the log mixing strength, and which is this. And this is experimental value. Of course, this should be consistent because I put 15% error in such a way that this prediction agrees with this experimental value. And then this should be consistent anyway. I should not say this as a prediction, but anyway. Okay, but also that, okay, this is a kind of prediction, okay, because the electromagnetic factor of ion is calculated in this way. Then you can calculate the charge radius by taking the low energy limit of this form factor. The charge radius is defined as a coefficient of p squared divided by 6. Then the charge radius of the pion is 3.8 over m squared. Okay, this is calculated using the A parameter and m squared. This is calculated in this way, and this is the predicted value. Okay, with 15% error here. Every scale with 50% error. That this is value, and this should be compared with the experimental value. And this is consistent. This is actually a prediction. Okay, let me talk only this subsection and then stop. Okay, let me briefly explain the chiral perturbation theory with hydrolocal symmetry. Okay, here, as I said, the hydrolocal symmetry is an effective theory for the Robinson and the pion based on the chiral symmetry of QCD. And in the chiral perturbation theory, with the local symmetry, we can make a systematic expansion, including the dynamical effect of the Robinson. And we can show that actually the loop expansion corresponds to the derivative expansion. And as a result, we can make a systematic derivative expansion of the terms in Lagrangian. Then we can say that this is a leading order, and these terms are next order. And let me show the expansion parameter. Okay, in the ordinary chiral perturbation theory of the pion, these are the expansion parameters, namely that p squared divided lambda chi square, and then pi squared divided lambda chi square. Where lambda chi is called chiral symmetry breaking scale and given by this form, 4 pi f pi. If you use a pi as an experimental value, you obtain this. Then actually the ordinary chiral perturbation theory just as an theory works until this energy region, but we know that exists in low meson, and the chiral perturbation theory breaks down on the low meson mass scale. But anyway, that this is a chiral symmetry breaking scale. In the chiral perturbation theory with hydrolocal symmetry, we have one more parameter, expansion parameter, which is given by this ratio. Then this is a low meson mass, which is about 770 MeV. This is lambda chi, chiral symmetry breaking scale is given by this form. Then one may wonder that this is not so small. But actually, this expansion is justified in the Lagrangian QCD. In the Lagrangian QCD, this Fi scales as an MC to the one, square root of MC. Then in the Lagrangian QCD, Fi becomes larger and larger. Then lambda chi becomes larger and larger. While the Robinson mass doesn't scale. Then this expansion, this parameter becomes very small in the Lagrangian limit. However, of course, this is true for any model. And this is not enough for the systematic expansion. For the systematic expansion, we need to show that this 1 over m rho does not appear at any level of the expansion. But this is of course guaranteed by the gauge invariance of the hidden symmetry. Okay, if you naively use so-called matter field method, if the longest propagator is given by this one, then you can imagine that this is a unitary gauge propagator. In that case, okay, M rho square appears in the denominator. Then you may wonder, this propagator may cause the existence of 1 over M rho square correction in a higher order loop level. However, in the hidden local symmetry, we can introduce a gauge fixing term in the gauge invariant. Okay, if you write this, that you can take this limit. This limit becomes well defined. Then this implies that gauge invariance implies that 1 over M rho square factor doesn't appear at any loop order. In that sense, that smallness of this expansion parameter is okay in the large energy limit, and this 1 over M rho factor doesn't appear in the hidden local symmetry because of the gauge invariance. This is order counting in the hidden local symmetry with the current partition theorem. And then the derivative is counted as order P as usual, in the current partition theory. And also vector meson is gauge coupling is counted as order P. This because that we want to regard this M rho square as small parameter. Then using this counting scheme, we can show that the loop expansion correct with the expansion. Okay, then this is an example of some order P4 term. Okay, means that order P4 means that the 4 derivatives are included. Okay, this alpha mu includes 1 derivative. Then if you have 4 alpha, then you have this. If you have 4 alphas in one term, that term includes 4 derivatives. Then count it as order P4. Okay. But anyway, this is just 80 terms. You have more and more. That actually we have 35 terms in order P4. Okay, I think that I should stop here. The next is this. Okay.
A few minutes. Questions. Is Akira here? You should have a question.
So, which value did you set for conformal mass in the action?
Okay, that is conformal mass, right? Conformal mass means that okay, that is unit mass, right?
Yes. And it should be close into the Pascal action of your excuse model.
Mm-hmm. I think that doesn't appear in my talk.
Okay.
That doesn't appear in my present analysis.
I think there should be an ambiguity for determining the conformal mass, and it is very important point for any excuse model.
Okay. Yeah, if you have some idea, I have no idea at this point.
I have a question. In the first part of your lecture, you mentioned that there's a problem between or a relation between the NQ, the clock mass, and the sigma, the condensate. And you said that these two quantities should be independent, and the problem comes from the IR boundary condition. So I think certainly the solution should be the relaxation of this boundary condition. So then you introduce this boundary term, this range fixed BT. So it means that it's a boundary condition. Okay, so it is equivalent to the non-vanishing of a boundary condition, right? Okay, so then what's the guideline to write down this boundary term? Otherwise, it will be arbitrary.
Yeah, that's, I'm not sure. Yeah, this is a, you can introduce any boundary term. Then I have no idea what is the guideline. But anyway, that boundary term should satisfy the gauging line. And that is the only guideline. Then this is some simple term, but why you don't have them the 6 next to the 6 order or something. Yeah, that's great. But maybe in my standard that I want to use only the simplest term. And this is one of the simplest combinations.
If I have other questions, I'll ask you later. So I don't see any further questions. So then let's just thank Professor Harada again. Any announcement?
We're going to take a photo. So everyone, let's move outside, follow the instruction of our staff, and we take a good photo. It take 5 minutes. Then we'll come back and have some dessert and drinks. Right. So we take group photo first. Let's move outside and we'll take a photo. Oh yeah. A break. A break. Yeah. And we'll have a break after the group photo.